Shall we continue our, as we say, voyage in the permutation models? Last week I talked about the Basic Fraenkel model. I'm using the terms as in chapter 4 of Yek's Axiom of Choice book. So the Basic Fraenkel model was really simple. We took a countably infinite set, we took the group of all permutations, and the filter of the normal filter of subgroups was the smallest one we could have. The filter needed to contain a few subgroups, and we stuck only those in, and that was it. What I mentioned last time was that I took a shortcut because of time constraints, and I want to take this longer route because it'll become important later on. Maybe today, maybe next week, but we're going to need that notion. So if you downloaded my notes of last week, I have to go back to page 4 of those. The thing that I want to talk about is how you get those normal filters. Is there a natural way of making them? And yes, there is one. We take a family of subsets of the set of atoms, a normal ideal, and the family is usually called I. Family of subsets, and what does it do? Well, it's like a filter, but upside down. Well, this is automatic, by the way, but let's see, I'll put it in the right order. So the elements of I are, shall we say, small. Because if something is small and something is a subset of it, then it's small as well. Ideals generally try to formalize the notion of a family of small sets. And the other thing is that the union of two small things is still considered to be small. We need to connect these to our permutations. Well, okay. Okay, let me complete the first line on the board. Making filters from what? Well, we give ourselves a set of atoms, and we give ourselves a group. And to determine the filter, we need something more. We could write down the filter, but we want to make the filter in an indirect way and use that indirect way to get it. And so we make filters from what? Our set of atoms, our group, and a normal ideal. That's going to be the main ingredient in in a few of our constructions. And that's where G comes in. Our family of small subsets is invariant under the axiom of G. So if something is small and I use G to chase it around the set A, I still get small stuff. And of course, all the singleton sets are deemed to be small. We're going to be using the I's, the members of I are going to be important in some of the later constructions. And also if you want to do this kind of thing in all kinds of other ways, it's quite often really more convenient to start out from an ideal rather than describe the filter itself directly. So, what do we need to define the filter? You may have guessed from what I did last week, because I sort of sneakily took the ideal of finite sets. Yeah, by the way, that's the example that we used last week was actually I was simply the family of all finite subsets of A, as you will see in a moment. So that's the smallest possible ideal you can have. You want all the singletons in there? Well, if I permute the singletons, I get singletons, so that's okay. And I want, if I have two sets in the ideal, I want their union to be there. And then the only thing you can get starting from the singleton sets is the finite subsets. But we had the symmetry we had the symmetry group already of our members of the universe, but the symmetry group can still permute the members of X. But the fix of X actually fixes all the members of X. So certainly this is a subgroup of F. No problem there, but the fix is generally much smaller. For example, I had the fix already in one of the exercises, I think, about the well-ordering thing. So the fix of A is just the identity. That's a set consisting of just one permutation. I think this is sort of the generally established notation for subgroups. We took what is our filter of subgroups? It consists of every subgroup that contains a fixed set for some member of the ideal. That's it. We take all the members of the ideal, we take their fixing subgroups, and we take all the subgroups that are bigger than those things, and that's our filter. And it's an easy exercise to check that that is indeed a normal filter. I didn't even do the homework on that, but for example, if you want to show that two of those fixing subgroups, the intersection is again a fixing subgroup, well, if a permutation fixes all the members of E and all the members of F, then it fixes all the members of the union and vice versa. So because E union F is supposed to be in I, the intersection of these two things is in F. And let's see. I think I have it in the right order. I'm taking this out of my head. But the fixing subgroup for pi E consists of the thing you get from the fixing subgroup of E by conjugating with respect to pi. Let's see if that works. Oh, wait. When rho is in this fix, if and only if this is in the fix. Oh, yeah. Right. If rho is in the fix of this set here, that means that rho has to fix all the things of the form pi a, where a is in E. Well, that means that pi inverse rho pi of a is always equal to a. That means that this thing is in the fix of E. But that means that rho itself, it's the pi times this thing times pi inverse of that, and therefore it is in the pi fix pi inverse of our E. And so on. You can just check that all the conditions for the filter have their counterpart in the conditions for the ideal, and vice versa. Now, why do we talk about this? Well, am I missing something? Is there no eraser?
fell on the ground, I think.
Well, fortunately, it's still here. Okay, so why do we even bother? Well, for one thing, it's nice to have a description like this, as we will see in a moment, and we get this. If we build our F starting from an ideal I, then we have a quite combinatorial way of checking whether something is symmetric. The combinatorial way means find a member of the ideal such that its fixing subgroup is part of the symmetry group of X. And this is the thing that we will generally always use. We have a symmetric thing, X. It comes with something from the ideal, and we know a fair number of permutations that will be in the symmetry group of X, namely those permutations that fix all the members of E. But, as we will see, and we actually used that last week, every permutation that does this is in the symmetry group of X. And of course, that is what we'll be using. If we want to prove something about X, we say, oh, there is a member of the ideal E such that if we know this, then we know that. And what are we going to do? We're going to permute elements outside of E. Those permutations will still keep X in its place. It will permute the members of X, possibly, but sometimes not. For example, if say X is a function and its domain consists of natural numbers, then every permutation will have to fix those natural numbers. Suppose, just by way of an example, suppose you have a function from omega, say, to A. And it happens to be hereditarily symmetric and everything. Well, then we know that there must be a member of the ideal whose fixing subgroup is inside the symmetry group of F. That means that What does this mean? Suppose I take two distinct members of A and of outside E. Remember, the members of I are small. Suppose, and of course, I take A not equal to B because why bother? Okay, and this is the cycle notation. So this is the permutation that only flips A and B. Okay? Because we only flipped two members outside of E. What did we see last time? In the kernel, the thing that we used, we started with the empty set and took the iterated power sets and everything. Every permutation leaves every member of the kernel invariant. That's why I took omega here. If I have a function from omega to A, and I have it has a thing. Oh, I didn't use the word yet. I was leading up to this important word. We call E, if that happens, we call E a support of X. So we have a support for F, but for every permutation, not only this one, pi of n is always equal to n. That's what we saw last time. The kernel, everything stays in its place under every possible permutation. Oh, wait a minute. All the first coordinates of the members of F stay the same. Well, every natural number stays in place under every permutation. Okay, suppose f of n is equal to a. I take a natural number, I suppose its value is a. That means that this ordered pair is a member of f. If I take its image under pi, it happens to be in pi of f. That means it's in f itself. Because now I'm using that pi leaves everything in E fixed. Lovely. But if I take the permutation of this, the image under pi of this, I get n comma b. I flipped A and B. Wait a minute. So n comma b is in F as well. We get a contradiction because our f was a function. What's the conclusion? Apparently, the image of f, the range, is contained in E. Assuming that E, the complement of E, has at least 2 points, this works for any two elements of the complement. So in this way, I can kick out any element of the complement from the image of f. So, this is another way, I think, of showing that I think it was in the homework. In our basic Fraenkel model had the ideal of finite sets as its starting point. Because what I said last week simply meant take the ideal of finite sets and take the corresponding normal filter. This shows that A is Dedekind-finite. There is no injection from omega to A. This is one of the ways of, I know that Dedekind-finiteness was on the program a few weeks ago, and this happens. You can prove Dedekind-finiteness also using some of the things I did that was in the homework. I think the official definition is every injective map is surjective from the set to itself. Well, using this idea, you can prove that as well. And the thing that you do always is permute stuff outside of the support, and that tells you that the behavior of the function outside the support is quite rigid. You saw this in the homework when I had the thing with the relation, and I took a finite support. Outside that finite support, the relation was really only just the identity or the complement of the identity, or the union of both, but that was about it. Because by flipping those points around, you can make sure that as soon as something is outside, everything is outside. And that's why the supports entered the language. Actually, the history was Mostowski introduced supports, and somebody later introduced the general case of filters. So supports were there first, and the filters came later. All right. What's next? So we had the basic Fraenkel model, and now I think I'm going back to my notes. Yeah, so our set of atoms is Dedekind-finite, but even better, the power set of the set of atoms is Dedekind-finite, and that's going to be homework. That's a little bit more difficult, but again, it's a good exercise in pushing sets around and everything. You say, well, wait a minute. If I have a map from omega to the power set, it apparently cannot be injective. And it's ideas like this that makes this work. By the way, when we do the atom stuff, the set of atoms could be Dedekind-finite, as we saw in the basic Fraenkel model. The power set of the atoms can be Dedekind-finite, as you will show for the basic Fraenkel model. Yes or no? Dedekind-finite? Who thinks yes? Who thinks no? And the rest doesn't think at all. Okay, I'm assuming our set of atoms is infinite, because otherwise there's no fun. For every n, you can take all the n element subsets of A. That's well defined, it's not empty, and it's different for different n. So there is an injective map from the powers from omega to the power set of the power set. Okay. Well, so that was basically about the basic Fraenkel model. Here is by the way, when I'm talking about the permutation models, the symmetric submodel, I can do whatever the hell I want. If I'm working in the model, I have to be very careful. We assume ZFA plus the axiom of choice in the universe, in the full universe with the atoms that we built last week. I have next week or the week after that, or the week after that, I'm not sure how I will plan this yet, I will actually show that starting from ZFC itself, you can prove that ZFA plus choice is also consistent. Okay, so if we assume that ZF is consistent, then we may assume that ZFC is consistent. Thank you, Gödel. From the consistency of ZFC, we can prove set theory with atoms plus choice consistent. So what we're doing here doesn't lead into trouble like that. Last week also somebody asked me, yes, but we were always talking about ZF and ZFC, and now we have those atoms floating around. Can we also show that axiom of choice is not provable from ZF? Yes, there is a way of taking such a permutation model, lifting it up a bit, and sort of embedding it in a normal model of set theory. And there you can get some of the bad behavior back in your, from the model with atoms, you can find that in the model of ZF. And in that way, you can use these results to actually prove consistency of a set without a well order with ZF. What I'm going to do in a moment, I'm going to give you a sequence of pairs without choice function. That can be lifted in that manner as well. And in the next hour, and probably it will take me some time, maybe next week as well, I will talk about a model where the set of atoms doesn't have a well order, so choice fails. But, and that was a question of Fraenkel's, every other set in the universe has a linear order. One of the exercises, I think in the homework last week was, the set of atoms in the basic Fraenkel model doesn't have a linear order even. But, so, and Fraenkel wanted to know, is that really sharp? Yes, you can have not well orderable, but everything else does have a linear order. So, the order, there is some order in the universe. Okay, but we'll go back to the, we'll go to the second Fraenkel model now. But the reason I mentioned that we will be assuming the axiom of choice is because I need it to set up some set of atoms, to set up some situation. Once I have that from choice, then I'm going to do the permutation bit and show that there is a small model where some choice is failing. Because in the basic Fraenkel model, the model itself, I could not do what I'm going to do now. We can do this easily because we assume that A is countably infinite. So in our big universe, what do we call that, V, there is a bijection between A and the natural numbers, and there is our splitting. This is just every time 2n and 2n plus 1. That's how we split A. This particular function will disappear after we've done all the permuting. It will not be inside the permutation model, but we have used it from the big model to set up the permutation model. That's how that works. So we split A into pairs, and what is G? We don't take all the permutations, we take the permutations that leave each and every one of those pairs invariant. You're going to see, you sort of guess where this is going. The members of the pairs are going to be indistinguishable, because we can always flip them around with a valid permutation. I will put a PDF on the website, and I shouldn't forget that to do that tonight, of an article by Bertrand Russell, where he discusses two things. Thing one is what everybody knows as Russell's paradox. The set of all sets that are not members of themselves is not a set. Well, that's not how he formulates it. It's good to actually read that to see how he talked about this. And the other thing, he has some remarks about the axiom of choice. And he discusses, in fact, this situation. He uses the metaphor of pairs of boots. He said, well, if you have a left boot and a right boot in your pairs, then it's easy to determine a choice function. Left boot, left boot, left boot, left boot, left boot. And when I first learned of this story, the other thing was pairs of socks. But when I read Russell's paper, he says, well, suppose you don't know, you don't have left and right boots. I thought, what? But that used to be the case in the old days. You just bought a pair of boots, and after wearing it for a while, one became the left boot and the other became the right boot. There was no specific left and right boots for sale. So it's possible that you don't know which one is the left, which one is the right boot, and then you don't have a recipe to pick a boot out of each pair. And that's the whole point of the axiom of choice. You have to have some kind of recipe to do your choosing. Your function has to be there, all ready to do the choosing simultaneously for you. And that means that somehow you have to tell it at every given point what to do. And if there is no distinguishing the boots, then you don't have a formula. Anyway, this is the group and the ideal. The ideal is just what we would think it is, the ideal, the finite subsets of A. So, I want to write this down explicitly. In the language of supports. So, just like in the basic Fraenkel model, when is something symmetric? If there is a finite set whose fixing subgroup is part of the symmetry group of X. But you can be very explicit here, because if AI is fixed by pi, then automatically BI is fixed by pi as well. Because that was, we want PI to be mapped to itself. So that means that the supports are actually unions of those pairs, automatically. So whenever you have a situation like that, you know exactly when a symmetric thing is kept in its place. Well, now we have to be careful. Of course, the sequence of pairs belongs to our big universe. The infinitely many, the ordinarily many power sets of A. But we need it to be in our symmetric submodel, because we want a sequence of pairs in our permutation model without a choice function. So we really want this sequence of pairs to be in the permutation model. Okay, well, this is no problem, because this is just a finite subset of A, and that is part of the model. And so the fact that we have a model of set theory will give us that. You can calculate the permutation thing, but in fact, let's see. In fact, every permutation keeps this pair in its place. Why? Well, every permutation keeps n in its place, but by definition, the pi of Pn is equal to Pn. Because we are sitting in the group that leaves all the p's in their place. It might flip them, but the pi of Pn is always Pn again. So the symmetry group of this is the whole G. And the same thing happens what is our sequence? Our sequence is, of course, this set of ordered pairs. This thing, the official definition is this. Now, so just like for the pairs, our sequence is invariant under every permutation from G. The permutation might flip the points AN and BN, but I don't care. It keeps Pn in its place. So, yes, this is in the model because the symmetry group of that thing is the whole of G, and all the members are in the submodel as well. Okay. Okay, let's take a break. Then after the break, I will show you why there is no choice function. And actually, I already gave that away. Look at the example that I had in the beginning on the left-hand and the right-hand side of one of those boards. And that argument is going to show that there is no choice function.